Thermodynamic cycles are divided into two categories. So let me just write it down. So thermodynamic cycles. I'm going to discuss the thermodynamic cycle itself in a minute. But now the thermodynamic cycles are either heat engines or refrigerator or heat pump. And I'm going to discuss one by one. The heat engine, its objective is to give heat input to cycle to get work output. Okay. The refrigerator or heat pump aims to input a work to make use of heat. Okay, so that is main difference. So now, in order to understand heat engines, we have to basically answer this following question. Now, please think about it. Can you really convert heat to a useful work directly? Okay. Now, let's try to think about this very simple experiment. And this experiment is basically the Joule's experiment. And what Joule did is he basically experimentally demonstrated that work can be converted to heat. Now, by looking at these schematics, we have paddle where that is immersed in the water. And let's say that you just rotate this paddle really a lot, very hard. You work very, very hard. Then, while you're working very hard to rotate the paddle inside the water, you measure the temperature of the water. Then, when you try to measure its temperature, then you can easily measure the temperature increase. What it means is that this work heat up the water, and because the temperature of water is bigger than the temperature outside, there should be a heat transfer from the water to the outside. So then we can understand that the work can be easily converted to heat. Now, can you really reverse this situation such a way? Now, can we heat up the water to rotate the paddle? Is it really possible? What do you think? Have you ever seen that you just apply heat to run this paddle? Obviously not. So in that case, you cannot directly transfer heat to the water to rotate the shaft. We are going to talk about it later, basically in the next lecture. This cannot happen because that violates the second law of efficiency, the thermodynamics. Okay. Then how can we convert the heat to the work? Because we want to do it. We want to, get some work done by the system by applying certain heat to it. Okay, so that is the basics of heat engines. Now, how can we make it happen? So the answer is that we need thermodynamic cycle devices. So not as this way, but we need a special thermodynamic cycle to convert heat to work, and that is our main objective. Then, what is the thermodynamic cycle? Please read page 16, page 165, and page 170 of the textbook to understand better about the thermodynamic cycle. But to make a very brief definition of the thermodynamic cycle, the thermodynamic cycle is a process or a combination of processes that make the system return to its initial state at the end of the process. So now what it means is that now let's start, your process or combination of a process is starting at 1. And now I'm going to change this one, B to A and A to B. I'm going to start with A. Now, from the initial state 1, then we move along the path, the process A to get to another state 2. And now from 2 to 1, then now we follow another path B to here the initial states. So when you make a closed loop, that is any kind of thermodynamic diagram, that is a cycle. Okay, and now we can think that as starting point 1. So starting state is 1. Now the final state or ending state is also 1. So now, can we really set up the first law of thermodynamics? How can you write the first law of thermodynamics for that cycle? Okay, so let me just write the basic equation of the first law of thermodynamics. So now we know that the final state, the difference of internal energy between the final state and the starting state or initial state can be written as Q minus W. Okay, so now I'm going to, if I apply this equation to that cycle, now the final state is same as the initial state. So now the change of internal energy of the cycle is always 0 because it does have the same starting state and ending state. Now that is same as Q, but in order to emphasize that is about all cycle, then let me just write it down as Q net. So if there is any different kind of heat transfer processes, then sum them all, that gives you the net heat transfer rate minus work net. So what you can see is that if you have a non-zero heat transfer into your system during the cycle, that can be converted to net work done by the system. Okay. Now, that is very important conclusion that we can convert heat to work in a cycle. Okay. Now, for heat engine, let's think about the network. So now, that network here is the net from 1 to 2, or work by following the path A, and the work by following path B. So that is the net work. Now, the work A is from 1 to 2. Still, we can write it down as PdV if you think that system as a simple system. Now from 1 to 2. Okay. So from this figure where you have work path from 1 to 2 by decreasing the volume smaller to V2, then we can say that this one should be negative. So what it means is that while we move from 1 to 2, where the volume at 2 is smaller than V1, then we need certain work to compress the volume. Okay? Then how about work at B? So that is from 2 to 1. Now we can write it down this way. But now in the case that is basically expansion. And expansion, it has positive value. So WB positive means that your system does the work to the surroundings. So that is the work that we need. Now, if you try to combine them together, but now based on the diagram we draw here, if the path B has moving up and down, and A is kind of from down to up, then its summation gives us this much of area. Okay, so now in the case, the net work, which can be shown as the area of the closed loop, is always positive. Okay, so in a cycle, there might be certain work, done to the system, and there should be certain work done by the system. But if we sum these two works component together, always the net work is positive in a heat engine. So that is the work we need, and that is the performance of a heat engine. Now, then, so in order to make heat engines, we need these 4 processes. So first process we should have is we need a heat from very high temperature heat source. This high temperature heat source can be, anything like a solar energy, boiler, and fuel combustion or nuclear reactor. Okay, so we need certain heat, transferred to heat engines from very high temperature heat source. Then we need another component or another part that that basically that convert heat to work. Okay, usually we have a rotating shaft. Okay, so this work is mostly due to the kind of shaft work. And after this engine does certain work to get some power out, then we have to reject the remaining heat to low temperature heat sink. Okay. In that case, the low temperature sink can be an atmosphere or river or ocean, like reservoir that has a lower temperature than the temperature of the heat engine itself. And they just keep making a cycle to keep running.